Welcome to our second lesson of Module 1, and in this lesson we're going to cover system and non-system fault definition, remembering that in our lesson 1 we did symmetrical and unsymmetrical, which was basically three-phase versus other unbalanced phase faults. Then we're going to look at fault statistics, and we're also going to be looking at the discrimination and grading of faults in a system. We start with a system fault, and in order for us to understand a system fault, we need to understand the definition of a system in our case. And for electrical networks, we're saying that that is where our primary electrical equipment is at, and we had defined those in lesson 1 as your transformers, your generators, your transmission lines, your distribution lines, or your cables, as well as your bus bars and switch gears. So that information we call our primary electrical equipment. So when we talk of a system fault, then we talk about if there should be a fault or any abnormality in our system, which can then result in failure of the primary electrical equipment. This then will require a disconnection of whatever equipment is associated to that primary electrical equipment, and it will be done by tripping your associated circuit breakers. So therefore, we first have to define what is our primary electrical equipment, and if a fault occurs or an abnormality on our system occurs such that it can result in the failure of that primary electrical equipment, then it means that we have a system fault. And how we overcome that, or how we protect our equipment against that, is the fact that we need to disconnect all affected equipment to that primary electrical equipment by tripping whatever is our closest associated circuit breakers to where the fault is being detected at. Then when we talk about non-system fault, we're now saying that it is something that is not happening on your primary equipment. The only thing happening on your primary equipment is that there is tripping of the circuit breakers, so therefore your primary equipment gets out of the circuit. But basically, what it is that your circuit breakers are being operated where there is no fault on the system. Therefore, they should not be operated because it's an incorrect operation. And they give, due to incorrect settings, a faulty or incorrect connection. But all of this is resulting around your circuit breaker. And it could be also from human error when they're busy doing their testing and maintenance work. So it's non-system because it's not on your primary electrical equipment, but rather on your protection, which is really mainly your relays and your circuit breaker. Then we've got our fault statistics, and there are two indicators that we utilize. That is the DSFP, which is the Discriminative System Fault Performance Index, and then we have the Non-System Fault Performance Index, which is an NSFP. So in the next slide is going to be showing how those get calculated. So all the records of your protection operations, they need to be kept, and they must be both correct as well as any incorrect operations that has happened. And we do this for the purpose of assessing the protection performance on an annual basis. And that annual basis performance basically is what gets measured for all of your electrical suppliers, so that we can be sure that their systems or networks are in good health and that they can perform well. And also we want to know that your errors in doing non system faults are very minimal, so that at the end of the day, your electricity is stable and it is reliable and almost always available. So for your discriminative system fault index, we have a formula that says A, which is the total number of system faults in a year that we are considering. Remember, it's on an annual basis. We subtract F, which is the number of system fault incorrectly cleared. Okay, so if it's saying it's faults that were incorrectly cleared, it means that it is faults that should not have been cleared, or rather it is faults that were really non-system faults, and therefore they ended up having to then be cleared. Then we have that will be A minus F divided again by L, A, which is your total number of system faults in that year, and then we get a percentage out of it. Then for your non-system fault performance index is going to be C minus E, and we divide the entire thing by C, and basically your C stands for your total number of circuit breakers that you have installed within your power system that has been defined, and then your E would be the number of non-system circuit breaker operations within that year. So you'll have your breakers, and then if any of those breakers operated for non-system faults, that will what your E is going to be. So now that we've looked at what constitutes our system faults and what we use to measure the performance of our networks, we now look at the aims of our protection scheme. So there's three aims really that we look at. And the first one is to make sure that our system gets protected against the adverse effects of a fault. And the second one really is to prevent our healthy equipment from being damaged by the fault. So if a fault is happening on a cable and that cable is going, let's say, to a motor, we want to make sure that we are at least protecting the motor by ensuring that we prevent that fault getting into the motor. We need to isolate that cable as soon as possible. And the last one is to reduce the damage at the point of the fault. So where the cable is the faulty portion, we want to ensure that if it is a 100-meter cable, that we don't have the entire 100 meters being damaged. So at the point of where the fault is, if the fault is about 30 meters into the cable from point A, then we want to make sure that it remains at that point. So we need to make sure we isolate the cable as soon as possible so that the damage on the actual cable becomes minimal and it only is really on the faulty portion of the cable. This will then make sure that we are able to repair the fault at a faster rate. Then we look at what we call discrimination and grading. So we first define what discrimination is, and really that is going to be your ability of a protection scheme to isolate only the faulty section of your power system. So if we looked at that cable that was going to your motor, we would want only that cable to be isolated. So in a scenario where you had an interconnected system, which you would have learned in the previous module on electrical engineering 3, and you had another cable that was feeding that same motor. So the one that has got a fault, if you isolate it, then you could still have some power going into that motor, which means that your load can still be operational. Then when we talk about grading, we really talk about the method by which discrimination is actually achieved. So it's how do we ensure that we are only taking out the faulty section of our power system. So that's what grading is about. And we've got different methods of grading, which is what the next slides are going to be about. So the first discrimination is looking at discrimination by time. And what discrimination by time really tells us is the time delay features get added onto your radial networks. Remember, radial was going from a source up until your load point. It didn't have any interconnected networks to it. So it's the time delays that we can get added onto the system, onto the fault current sensing your devices in your relay. And if you're looking at the sketch that they basically have over here, you can see that at bus bar A, you've got two breakers that are looking in there. You've got a breaker on bus bar B that is at below your bus bar. And then you've got one at C below and another one at D below. So what would happen is you've got this lightning strike that you see here, which is between your C and D bus bars. And from that point on, you can see that your first breaker, which was the one below D, it had no added delay. You would expect it to immediately trip once it senses that there was that fault. Then your breaker that is just below C is set at 0.4 seconds in this case, delay time from what your breaker D is. So what it means is that if the relay at D, for whatever reason, didn't operate, maybe it's malfunctioning, then your breaker C is the one that needs to take out this fault, but it will only do so in 0.4 seconds after the time that breaker D was supposed to have taken out the fault. And then we keep on adding the delay as we go to breaker B, because now breaker B is 0.8 seconds, and that 0.8 seconds again is looking at it against your breaker that was sitting at D. So if D did not operate and C did not operate in that 0.4 seconds, then at 0.8 seconds, your breaker B will be the one that operates and isolates this fault that is over here. Then obviously at A, you can see that the delay is now at 1.2 seconds. So this type of a scenario on its own has got a disadvantage. And the disadvantage really is that the relays that are closest to your source, those are the two relays that are closest to your source, they will take the longest time to clear the fault. As you can see, it's 1.2 seconds that has been added to clear this fault over here. And that will result in damage that can be done onto your network to such an effect that it could even come and damage your generator that you have at your source point. So that is the disadvantage of it. A lot of fault current will come and develop here, which is very close to your source by the time that this network operates. The second one is discrimination by current magnitude. And on this one, we're really looking at the impedance, and we're looking at the impedance from your source up until to where your fault is. So looking at the first fault, which is F1, you can see there that the impedance we need to consider would be the impedance of your source, which is the 0.485, and then we would consider the impedance between J and H. But unfortunately for us, the fault is not after OH. So it would not be that entire impedance of 0.24. It would be some percentage of that impedance that we would get at F1. Then if you look now between F2 and F3, between OH first and your transformer, you can see that the impedance of that line is 0.04 ohms. And then for your transformer, you've got the 2.12 ohms. So if you're looking now between your F2 and your F3, can you see that you are sitting at exactly the same point where you are experiencing firstly the Z source, which is a 0.485, and then you're experiencing the Z between your J and your H bus bar, which is 0.24. So you add that in here. But then between these 2 points, the difference is so minimal because they're right close to each other, F2 and F3. So the impedance there could be 0.04 on any one of them. So the advantage here, we say that it's not a practical solution. as when you have distances between 2 points that are too short, like your F2 and your F3, then it's difficult for you to really constitute on where the fault is and are you tripping out the correct associated equipment at the right time on it. So our third method is discrimination by time and direction. Looking at this network that we have here, you can see that we've got a source, and then we've got a bus bar at A, and then we've got bus bars B and E and bus bars C and D. What we need to first realize is that they introduce non-directional relays, and non-directional relays basically means that they can pick up a fault either on the bus bar above the relay, or they can pick it up below your relay, so going towards your E in this case. And if the fault is introduced where this lightning strike is at, which is between your A and your B bus bar, the fault current will have two paths in which they flow. The first one will be going down from that fault, going down towards bus bar B and all the way around. And your other one will be going through your bus bar A. So those are the two fault current paths that can be done or achieved in this network. Now, the problem with this is that proper discrimination can never be really obtained because you are going to have at the bottom fault path, you're going to have two relays that operate, that is your C and your D. They'll both operate because they are both at 1 second compared to your B that was at 1,5. Now, the reason that we're saying that discrimination is hard to obtain because two relays are operating instead of one. As well as if you look at your top part, you'll also have two relays operating there, which are both at bus bar A on either side at 2 seconds there. Again, that's why the discrimination is not very clear. Because if you're sitting as an engineer in an office or in a computer and you're trying to see where did the fault occur, it would be really difficult for you to determine because the fault could have occurred on this point to talk to these relays both operating, or it could have happened at this point to talk to these two relays that are being operational. Then the next one, we talk about discrimination by time and direction. So now, instead of having the non-directional relays alone that we had on the previous example, which we still have here, we've now introduced over and above that what we call directional relays. And what are directional relays are? So directional relays are now only looking at the fault of where your arrow is pointing. So you can see at B and at E, the arrows are pointing down. And at C and D, the arrows are also pointing down. So what it means is that they can only pick up the faults that are coming in those directions. So your fault at AB, which is still exactly in the same place that it was before, your infeed relay to B, can you see that it's sitting at 0.1 second? We didn't have it initially there. It will now trip the circuit, and the relay at A will be the one that also tripped the circuit that is going up. So your two fault paths, the one going down gets tripped now at B in that 0.1 second. And remember, in the previous one, it was getting tripped at C and at D, okay, at only 1 second. And then the top part is still the same because it's a non-directional relay that is in there. So we say the advantage over here is that no supplies to any loads will be lost, and proper discrimination is obtained between all the relays. Why are we saying no supplies to any loads will be lost? Because if your faulty section is over here and there is your source, our loads at E will still get supply, our loads at D will still get supply, our loads at C via this path will still get supply, and even our load at B via that side will still get supplied, and only this portion will have broken away from the network. Then the last discrimination that we have, we call it discrimination by distance measurement. And this one really, we talk of the distance protection relay, which monitors the impedance of the line in proportion to the distance of that line. So we divide our line into what we call zones, and we have a zone 1, a zone 2, and a zone 3. Your zone 1, we say, would cover 80% of the line, it can protect it, whereas your zone 2 would be at 120% of an identified line, and your zone 3 would go up to 150% of that line. So looking at the diagram that I have over here, can you see that I've got 3 substations or 3 bus bars? I've got one at A, I've got one at B, and I've got one at C. So my zone 1, you can see that it goes from A up until just before you get to B. So that would represent the 80% of my line. Whereas my zone 2 goes beyond B and covers a portion of the line between B and C. So we say that it has covered the line 100% from A to B, and then we add 20% of the distance or impedance of what the value of A to B was. We add it now onto this part, and that is how we get the 120%. It's not 20% of the line length between B and C. Then for your C, it becomes zone 3, it becomes 150% of the line. In other words, if this was my 100% of the line between A and B, then 150 would be half of between A and B. We take that and we add it to this side, and that is how we get our zone 3. So now we're going to go into a little bit of a questionnaire just to make sure that we understand or we know what we have just captured. So the first one, you've got an example there where they say we must identify if these are either system or non-system faults. So the first is saying you've got a technician in the control room that mistakenly opens a line feeder breaker. So the fault is not happening out on your primary electrical equipment, it's happening by a person that is making a mistake, so it becomes a non-system fault, and the reason is because it's an incorrect operation of the associated circuit breaker. Then the second one is you've got rats or rodents, and they short circuit and trip the circuit breaker or the feeder. So again, it's happening at the circuit breaker and not at our primary electrical equipment. So therefore, it also makes it a non-system fault for the same reason. Then the third one, it says that we've got an eagle, which is a bird, and it short circuits the phases of your transmission line. Remember, a transmission line was one of our primary electrical equipment. So therefore, by default, because there is a short circuit that is happening in there, regardless that it was done by a bird, it means that we now have a system fault. But also, if you remember, we did say that these large birds are what causes 10% of our permanent faults in transmission lines. So this becomes a system fault because it's happening on our main equipment, and the fault or system abnormality that happens there, which is the short circuit, will involve failure of our primary electrical equipment. Okay. Then we move to the next one, and that is your cable joint failure. And the cable joint failure is also on the cable, and the cable is part of our primary equipment. So therefore, it's a system fault because that causes an abnormality on that primary electrical equipment. Then we look at number 2, and this really talks about symmetrical, the difference between symmetrical and unsymmetrical fault. And this we did on our first lesson that we did. And basically the difference was that symmetrical looks at all 3 phases the fault occurs. And so it is a balanced fault system, either with or without an earth. Whereas in unsymmetrical, we say it's an unbalanced fault because it either happens only on a single phase or only on 2 of the phases. It's not happening on all of your 3 phases. So it can also be with or without earth. Then they say we must now discriminate between a system and a non-system. That's what we've learned today. And really, a system and a non-system says that a fault or system abnormality that results in your primary equipment failure would become your system fault, where you are now forced to have a circuit breaker that needs to take out that faulty section. Whereas a non-system would be an incorrect operation of a circuit breaker where there are abnormalities on your primary electrical equipment. I just want to cover something that another student had asked me before. How do you correlate between your symmetrical and unsymmetrical fault with your system and non-system fault? Okay, so your system fault, it can be symmetrical or unsymmetrical, all right, because it's happening on your actual electrical main equipment, and it could be a balanced or unbalanced fault as long as it's happening on your actual electrical equipment. So it is a symmetrical, your system fault would be a symmetrical and a non-symmetrical fault. Whereas your non-system fault would not even really talk about symmetrical or unsymmetrical because it's happening at your operation, at your circuit breaker, and your circuit breaker just takes out everything. So if you wanted to link it to your symmetrical and unsymmetrical, it would probably be your symmetrical because it would take out that entire equipment. Am I making sense? Then one of our last questions is, if you've got an 11 kV system where you've got 120 breakers, and they say that the relays in this system operated 40 times in this 1 year, and when it operated when no faults were detected on the feeder. Then they say there were 80 system outages reported on the system, but only 63 of them were registered on the events recorder, and they want you to determine the discrimination system fault index as well as the non-system fault index. So looking at this, the first thing that you do, you go put on the formula. Remember, there was an A minus F divided by A, and you times it to get your percentage. And your A was your total number of system faults in a year. So in this case, the total number of system outages that happened in a year, although it was 80 for the outages, but only 63 of them were registered on the events recorder. So it means that they only register your system faults on the events. So therefore, it's 63 is equivalent to A. And then for your F, which was the number of system faults incorrectly cleared, we go on and we say that number is the 80 that talk to your system outages, and we subtract the 63 that were registered on the events recorder so that we can get what that difference is. And that difference would then constitute F, which is your number of system faults incorrectly cleared. So they were incorrect faults. They were not system faults. That's why they were then incorrectly cleared. And we have there 73%. Then the next one, when we're looking at our non-system fault performance, we remember the formula, which is C minus E, and I divide by C and I times by 100%. And really our C was the total number of circuit breakers installed on a power system, which is 120 in this case. And our E was the number of non-system circuit breaker operations in 1 year. And that number is 40 because it says relays operated 40 times in 2017 when no faults were detected on the feeder. Then you divide by the 120 and you get 66.67%. And that, ladies and gentlemen, is the last slide of our lesson 2. We are basically left with 1 or 2 more lessons of the first module, and then we can continue to our other modules. Thank you very much.